Hello everybody, in this lecture we will be solving 1973 IMO problem number 3. Here is a view of this problem. Let A and B be real numbers for which the equation given as such has at least one real solution. Okay, for all such pairs A and B, where A and B are obviously these coefficients, find the minimum possible value of A squared plus B squared such that we have that one real solution. We should have at least one real solution. Okay, so we have a quartic polynomial, and I assume you guys are familiar with how to solve a quartic polynomial by simply reducing it to a quadratic form, and pretty much the same holds for cubic polynomials as well. More or less, there are some certain tricks. One of the tricks is to consider the following substitution: y is equal to x plus 1 over x. Now, before I do this substitution, let's and here y is a real number. Let's just expand it. So that would be xy is equal to x squared plus 1. And rearranging it, finally we get x squared minus xy, or yx, let's say. Here y is like a coefficient. Yx plus 1 is simply equal to 0. So this is a quadratic expression in x. We can simply apply the quadratic formula and find the roots. But one thing is for sure. So for this to have any real roots, x, if and only if the discriminant, and the discriminant in this case would be, remember, b squared minus, so that's minus y squared minus 4ac, 4 times 1 times 1, so that's simply y squared minus 4 is greater than or equal to 0. Or you can simply write this as, if you will, y squared is greater than or equal to 4, so taking the square root of both sides, y in absolute value is greater than or equal to 2. So we shouldn't forget about this condition, which is the critical condition for the solution of this problem. Now let's go ahead and start with our quartic polynomial. I'll just first divide both sides by x squared. Well, actually, one more thing before I go to that. This would obviously imply that if I square both sides, here I would get y squared is equal to, this is the square on the right hand side, would give us x squared plus 1 over x squared plus 2 times x times 1 over x, which is just 2. Okay, now going back to our quartic, so let's divide both sides by x squared. Then I would get the equation becomes x squared plus ax plus b plus a over x plus 1 over x squared is equal to 0. But then I can simply bundle together similar terms. X squared plus 1 over x squared is obviously y squared minus 2. So this implies x squared plus 1 over x squared is y squared minus 2. So I have a y squared minus 2 here. And then I have ax plus a over x, but x plus 1 over x was y, so that's just a y. And finally I have a b here. Plus b is equal to 0, and let's organize it one more time before, so therefore I get y squared plus ay plus b minus 2 is simply equal to 0. Let's apply the quadratic formula again. So if I apply the quadratic formula, actually, at this point there are two variations to solve this problem. You can either use well-known inequality tricks, or you can directly use the quadratic formula. Let me show you actually both tricks, and you can check AOPS forums to see even more stuff going on there. So using the quadratic formula, y the root, by the way, y would be equal to minus a plus minus the square root of the discriminant, which is a squared minus 4 times b minus 2, all divided by 2. And recall that y itself is equal to x plus 1 over x. So right, so the condition that we ensure that at least one of the x is, remember here when we started here, the condition that at least one of the x is real was that y was, so the absolute value of y was greater than or equal to 2. So that translates as, if I take the absolute value of this whole thing, so taking so the absolute value of y, so absolute value of y is simply equal to 1/2 the absolute value of minus a plus minus the square root a squared minus 4 times b minus 2. So we need this expression here, there's no 2 here, to be greater than or equal to 2. We can move the 1/2 to the other side, so that would give me a 4. So this implies that for at least one of the roots to be real, you should have the absolute value of y to be greater than or equal to 2, as we said. And now we can expand it, and then so at least we should have the following thing, right? So the absolute value of a plus the square root, this expression here, a squared minus 4b minus 2, that thing would be greater than or equal to 4. So we need to ensure that this thing at the least holds, which implies that the square root of a squared minus 4 times b minus 2 itself is greater than or equal to 4 minus absolute value of a. And I can just simply now square both sides, so squaring, I would get a squared minus 4 times b minus 2 is, well, because both sides are positive, greater than or equal to 16 minus 8 absolute value of a plus absolute value of a squared, which is just a squared. And yeah, I can simply cancel out the a squared expressions here, and then both sides are multiples of 4, so dividing by 4 I would get some 2 minus b, I think, on the left hand side, greater than or equal to, dividing by 4, 4 minus 2 absolute value of a. So I can simply move things around, so that would imply 2 absolute value of a is greater than or equal to 2 plus b, I guess. And now I can simply square again, so squaring again, that would give me 4a squared is greater than or equal to 4 plus 4b plus b squared. Yeah, I can, let's go ahead and add 4b squared to both sides of this expression, because remember we need an expression for a squared plus b squared. So add 4b squared to it. This would imply 4a squared plus 4b squared is greater than or equal to 5b squared, because b squared plus 4b squared. So we have 5b squared plus 4b plus 4. But if we further divide both sides by 4, this would imply that a squared plus b squared is greater than or equal to having let's do it in 2 steps. 5 over 4 b squared plus b plus 1, and then I can just factor out the 5 over 4. That would give me b squared plus 4 over 5b plus 4 over 5. And then finally I just observe that on the right hand side, so I can do the following trick, the squaring trick basically. So I can think of it as, so this one is a perfect square. To make it a perfect square, so this is 2 times 2 over 5, so I can just add and subtract the components. So let's do it. So I have b squared plus 2 times 2 over 5b plus 2 over 5 squared minus 2 over 5 squared, so that's simply 0. I can do that, plus 4 over 5. Now finally we get 5 over 4, and then on this side we have b plus 2 over 5 squared, right? And then I have this expression here, so plus 4 over 5. And finally we are done, because obviously this expression here is definitely greater than or equal to 0, being a perfect square here. So this whole thing is greater than or equal to 0, suggesting that a squared plus b squared have to be greater than 0 plus 4 over 5, which is just 4 over 5. So therefore the minimum value that a squared plus b squared can take, so that we have at least one real solution to the given quartic, is 4 over 5, and that solves the problem. I highly recommend you check on AOPS discussion forum to also find some alternative solutions like Cauchy-Schwarz. The Cauchy-Schwarz inequality solution is pretty nice, so you won't have to use the quadratic formula, but it's basically the same thing. But yeah, hope you enjoyed this lecture, and looking forward to see you guys in our next lecture.